thank you all for welcoming me here. I'm Olivier Tonneau. I'm a partner and co-founder at a VC fund called Quantum Nation. I founded this fund 8 years ago with my fellow Christophe Jurzac, who is a quantum PhD. We've been investing in quantum technologies for the last 8 years, and what we have witnessed is tremendous acceleration. So today, I'm going to tell you the story, because quantum is sometimes perceived as a perpetual 5 years technology, meaning it's always 5 years from happening, but never delivers. Now I'm going to tell you how it took 100 years to get to where we are, but now it's starting, and it's starting in real life. And it will have applications to fight against climate change. It will have applications to find new drugs, maybe proteins, who knows? And first, I would like to thank the organizer to have me here in Oxford. Oxford is it's an incredible place. Science has been studied here for centuries. Some ideas here, which is a nice concept, are left unfinished. And the next generation will pick from that and build upon it. So it doesn't sound unreasonable to talk about quantum being 100 years old and evolving in such a place. Now, let's see how quantum started. It did not start to become a startup. It did not start to build product. It started as a crisis. Crisis why? Because in the 20s, the physicists, the great mind of the time, Einstein, Planck, Niels Bohr, they were looking at things and seeing that just the world did not behave like classic physics said it should. They had to find an answer. The energy came in packets, the particles came in wave, and looking at that destroyed everything. So they came there was a very famous series of conferences which are called the Solvay Conference that happened early in the last centuries. If you look at this picture, 1927, the most brilliant minds in quantum physics are on these pictures. Probably the picture with the most IQ ever. You can see here Max Planck, you can see here Marie Curie, Paul Dirac, Albert Einstein, the GOAT, no need for introduction. You can see Heisenberg, you can see Schrödinger. By the way, I learned this morning that Erwin Schrödinger was a member of Magdalena College here in Oxford. So again, one more good reason to speak here. Heisenberg, Niels Bohr, they were debating about very fundamental things. The questions that they were trying to solve were questions like, is information traveling faster than light? Can we send information more rapidly than the light can transmit information? Is the world deterministic or is it probabilistic? If we look at the nature, does it change the structure of the nature? So those were all very fundamental debates. It culminated in a series of arguments between Niels Bohr and Albert Einstein. They disagreed very violently for years. Niels Bohr was of the idea that the world was profoundly probabilistic, random in some way, and that when we look at things, we change their nature. This was something that Einstein could not bear. In his mind, the world was deterministic. And if we could not find determination in the world, then that means there must be some hidden variables that can explain that we have not yet uncovered, and that can explain why we are not seeing the world as it behaves. So it was, for decades, arguments, pure arguments of theory. Now, I will go a bit into the theory. I will not lecture you on what is quantum. First, I'm not a quantum physicist, and plus we only have 15 minutes here. And maybe I sense some relief in the room that I'm not going to do so. So I will start. Those are the quantum properties. I will come back to that later. But first, you have to understand that quantum mechanics and quantum technologies is about playing with individual particles, elementary particles. What are those particles? The first one is atom. Atom is the building block for nature, for everything, for matter. There's a nucleus, there are electrons going around, and that's the basic for building every matter that we have on Earth and in space. The second one would be electrons. Electrons are electrically charged, so that's how we get the power. Electrons, being able to control thousands of electrons gave us the information age technology, gave us computers, gave us the ability to compute and the internet. The next one, next elementary particle would be the photons. Photons is the smallest grain of light you can imagine. They carry information, they have no mass. I mean, how easy is that to understand? I have trouble to conceive that. But photons, if you consider thousands of them, we have laser. If you consider the smallest one of them, then we can start doing special things with quantum physics. The last one is ions. Ions would be an atom that has lost or gained an electron, so giving them very different properties than the classical atoms. Now, what are those strange quantum properties that I've come to fall in love with? Because they are so surreal, it's really so different than what we can imagine today. It's in some way inconceivable, yet it has been proven that it works. The first one would be superposition. In the quantum world, at the elementary particle level, an atom can be in several states simultaneously. And I will show you a famous experiment that was done to illustrate that later. So, quite incredible. In the classic world, you have your bits, and it's either 0 or 1. In the quantum world, you have your qubits, and it can be many things at the same time. From that, we derive a very important property, which is the ability to compute with exponential power. If you have 100 qubits, and you just add 1, you go to 101, then you double the computational power. So I'll let you imagine what does it make if we have 1 million qubits in a computer. This will surpass anything that we have in terms of computation power with the classical machines. The second one is entanglement. This one, probably also one of my favorites, so difficult to understand, but that's how it works. So typically, if you take two entangled photons, meaning they are kind of twin, you have one there, you send another one thousands of kilometers away. If anything happens to one, the other one will know right away. Not even at the speed of light, right away, at the same time, simultaneously. That's so amazing, and from that, we can typically encode communication. We will send packets of data over fiber. We will send entangled photon along the way. If your data is intercepted, then the photon will know, and then you stop the information flow, and you're protected. So, quantum physics will also be about protecting the data in the networks. The last one is measurement. When you measure a quantum state, it's very fragile, so it disappears, it collapses. So what makes it difficult to make a computer, because keeping a particle in the quantum state is complicated, makes for very good sensors. Because if a qubit is very sensitive to its environment, then it will sense electromagnetic fields, it will sense the pressure, it will sense a lot of things. So that's also, from these three properties, we will get quantum computing, quantum communications and networking, and quantum sensing. Now, to illustrate what is superposition, Schrödinger, so from Magdalena's college, he imagined an experiment which is called the Schrödinger cat. This is my personal interpretation of the Schrödinger cat. So the idea here, to make you realize what it's about, is if you put a cat in a box with a vial of poison and food, as long as you don't look at the cat, it is both dead and alive at the same time. Now, if you observe, the cat will choose one of the two states. And that's explaining how, in the real world, superposition works. As long as you don't measure the atoms, they are able to explore a lot of positions. So that was from the theory. Now, how did we get to the first theorists? So it was 1920s. Now we are getting into the 1970s, 1980s. The arguments are starting to settle. Now the question is, we have theory, but how can we prove that it's real as long as we have not done experiment to show it works? And this started in the 1980s. The first guy who imagined a quantum computer was Professor Richard Feynman, Nobel Prize, and he said, well, if the nature behaves randomly, and if the nature behaves like quantum, then the best way to simulate and understand nature would be to build a quantum computer. He was the first to think that we can build quantum machines. The second one right after was Alain Aspect, by the way, the godfather of our investment fund. Alain Aspect in 1982, he did an experiment that proved entanglement in his lab. Like over 50 meters, he managed to create entanglement. It was quite a revolution at the time, and he was the one who proved that Niels Bohr was right and Einstein was wrong. But 60 years after. From that, other people emerged, new ideas came. Arthur Eckert, he was the first to think that using entanglement can be good for quantum encryption. And from that, it started to unfold, it started to develop. What has happened since, so we had the era of the theoreticians, the era of the pioneers, the first one to experiment and to test. And what's happened in the last 10 years is that we are now coming to engineering and industry. What was lacking for quite some time for quantum to progress, and for now having a lot of progress all at once, was new technology. We need lasers. And now lasers are getting more stable, more powerful. We needed cryogenics, because a lot of those technologies have to operate at close to absolute zero temperature. And now we have cryogenics that can be the dilution fridges that can be used in order to study the effect of quantum matter at close to absolute zero. We needed also some fast electronics, we needed error correction, and this started to happen, and as long as it happened, now it's removing the frontier for engineering quantum technologies. So now, what does a quantum computer look like? This is a quantum machine from Pascal on the left. What they are using is what we call neutral atoms. So they are playing with single atoms. They are in a vacuum chamber, and how do? We are capturing and trapping the atoms thanks to what we call optical tweezers, which are in fact lasers. And then we are starting to play around and make computation. It looks just like now a typical server in a data center. That's to show you how now these things are starting to be engineered. It's out of the lab. There's about 100 quantum computers in the world that are now in data centers and working alongside other computers. We have this one on the right here is a local one, Oxford Quantum Circuit. It's called the Quantum Superconducting Computer. What you are seeing here is basically a dilution fridge. So that means it's designed to get the temperature close to the absolute zero at the bottom of the fridge. And then your computer will be a 1-inch chip that will do the computation. Because when you get too close to absolute zero, then the matter is more easy to control. So those are just examples. There are other ways to build quantum computers, but those are nice ones. When telling you about how we can now manipulate single atoms, this is a good example of what's happening inside the Pascal machine. We are trapping single atoms, and we are able to put them in any kind of form that we want, even an Eiffel Tower here. So what will happen next? We have now tens of billions that are invested in those technologies. We have thousands of people who are working in that field, a lot of them in Oxford here. IBM has put online the first qubit 10 years ago for people to start playing it. You can access the machines over the cloud. So all this now is self-reinforcing and accelerating. So those machines, they will be good for, a quantum computer can do 3 types of computations. The first one would be large optimization problems. And this has applications in the finance industry, in the logistics, in industry. So typically, if you were able to better optimize transportation, then the gain in terms of CO2 is immense. Just 10%, 5% would have a tremendous impact over CO2 emissions. With quantum computer, the second class of problem you can tackle is simulation. So simulation will bring new molecules for energy transition. We are thinking about quantum materials for energy transition and for new batteries. We are thinking about how to develop new drugs. And we are thinking about how to better simulate the flows. So typically computational fluid dynamics with application in the aerospace and automotive industry. All this is going to have an impact on our everyday life. Quantum communication will help us protect our data. It will help us regain property over the information that we are transmitting. And the quantum sensors will have application in medical imaging, in being able to do some geolocalization without using GPS. So a lot of very precise sensors that can help improve a lot of what we do today when the classical technologies hit a wall. So the thermodynamics gave us the first industrial revolution. Mastering the electrons gave us the information age, internet. And I believe that quantum will bring the new industrial revolution. So it took 60 years of theories, 30 years of first experimental pioneers, and 10 years of industrial development. Now, do I think that quantum technologies are 5 years away? I don't. It's coming now, and it's going to be a true revolution. Thank you for your attention.